polynomial. So phi sub I of z is a product of z minus ci. Ci belongs to ai. So thus, for each set, is thus this product.
And the prime is a derivative?
And yeah, and prime, and even though I don't like derivatives and being discretian, so for me it's not derivative. For me, definition. No. A continuous guy like you would say, and that's how the paper is in result, is a derivative at C1. But being a discretian for me, this is that notation, phi prime of Cj, of C. Sorry, not Ci. Yeah, it's better than this. Okay. It is phi of Z divided by Z minus C evaluated. This is my definition. The complete algebra, the derivative. But if you like derivative, that's okay. What is it good? It tells you a way to find the certain coefficient of this. All you have to do. It looks like the original is better than this huge multi-sum with d1 plus 1 times d2 plus 2 terms. But let's first see how it's applicable here. Here we have constant term. So first we have to make it into a polynomial. This is a Lorant polynomial. Reminding you, let's do x sub y, q, y over x is a Lorant polynomial in x and y. So spelling out 1 minus q x1 over y, spell it out, 1 minus q to the power a minus 1 x over y times 1 minus q y over x to the 1 minus q to the power b y over x. It's a Lorant polynomial. It has a positive and negative polynomial. To make it a genuine polynomial, all you have to do is multiply by x to the power a, y to the power a times x to the power b. They become a genuine polynomial. So you can reformulate the q-Dyson conjecture instead of constant term is find the coefficient of x1 to the power a2 plus an, x2 to the power a1 plus a3 plus an. So in general, a formulation is, if we call sigma the sum of the a's, is x1 sigma minus a1 and up to sigma n. And now you put here x sub j to the power ai and x sub j to the power ai, x sub I to the power j. Now it's a genuine polynomial. It's no longer a Lorant polynomial, and now it's no longer constant term. It's some genuine thing. So now this is applicable. You can easily see that the degree is indeed exactly d1 plus d2 plus dn. So if we let d sub I, if we let here d sub I be sigma, if di is sigma minus ai, in other words, a1 plus a2 plus a minus 1 plus a sub I plus 1. If you let this, you can see the degree. It's an easy observation. So this is exactly applicable for this. The only thing that remains to do is to find a clever, judicious choice of a1, a2, an. If you take a random choice, you get a monster. you get a huge sum over d1 plus 1, that's d2 plus 2, set. But this is not just an ordinary polynomial. This is a very nice, good-looking factored polynomial. And hence, with a good, clever choice of the set A1, A2, AD, this hope that most of them would become 0. You don't want all of them to be 0. You don't want all of them to be equal to 0. Then you disprove the q-Dyson conjecture. Then it will be 0. So all you have to do is come up with sets A1, A2, AN that very few. And it turns out, with a good choice of the sets A1, A2, again, if you plug it in, you get only one term survives. And this explains where you get closed form. If it will be few terms, it will be a little bit messy. That's the reason we get a nice Q multinomial coefficient here that I raised. Because only one term survives. And here it is. And the rest is an exercise. That's to the reader. Here is the choice of A1. And the rest is that routine multiplication. In fact, my computer can do. The paper has the details. So A1 is a set 1, Q squared, Q, sigma minus A1 plus 1. Sorry, plus sigma A1. What I call D1. So of course, if you start with 0, the cardinality of A1 is D1 plus 1. D1 is sigma minus A1. And similarly, A2, 1Q, Q squared, Q sigma minus A2. This is a clever choice. It's not that clever. I mean, it's pretty obvious. That's the first thing I would try. A set of erasing Q's. Since you have Q's in, it makes sense to have part of Q's. And the most dangerous thing. So basically, it was observation that this brand new quantitative form of the Commutator-Nussel ansatz is applicable to the famous Zeilberger-Bressoud theorem. So it's essentially a very clever observation, but it's observation. The rest is are details. So 1Q. It's beautiful, don't get me wrong. And now it's an exercise. If you plug it in, for most, so it's a Cartesian product. Cartesian product for most of them, for most choices, from here, from here, from here, from here, it will be 0. The only exception is the following. The only thing for which this, when you plug into the polynomial f, this is my f, and this is as follows. Here goes. Sorry, blanking out. Yeah, it's this. And one. Yeah, here. Yeah. You take this. Yeah, so the point. 1 comma QA1 QA1 plus A2 QA1 plus A7 minus 1. This is the only survivor. It's a nice exercise, but not too bad. That everything in this huge Cartesian product, the only survivor is this that gives you a non-zero thing. And then it's an exercise to evaluate it, and it's an exercise the computer can do to find it exactly. So this is really the proof. Okay. So this is very nice, very elegant, but also depressing. At least by hindsight, it's completely trivial. It's nice to prove some non-trivial results. So it so happens that the constant term is very, very nice. But what's so good about the constant term? What about the coefficient of x1 to the power 5 times x2 to the power 11, x3? Find some other coefficients. What's wrong with them? So my observation was to rescue it from triviality and make the computer do some work. To generalize this method, not just for the constant term. So in this term, you have a fixed vectors. Before it was 0, 0, 0. So it's perturbation of the q-Dyson. By the way, a few years ago, my former postdoc, Doron and myself started the question of computing other coefficients. And we named our paper Disturbing the Dyson conjecture in a good way. As an allusion to his famous book of essays, Disturbing the Universe, and to the proof of IJ good in a good way. So we use the technique of IJ good for the original Dyson conjecture to get other coefficients. Then Doron, my disciple, found Q analogs, conjectured Q analogs, and some smart Chinese people, including Zin, that I mentioned before, and two students, proved them using the complicated method of Gessel and Zin. And I realized that these things, this same technique of the two Hungarians, could be used to find disturbed latency. The same techniques works. But now, if you look at the list of survivors, it's no longer a singleton, but still a finite set. And nothing gets complicated, and you had to write a computer program that inputs data 1, data 2, data n, and outputs the set of survivors. So that we get non-zero in this huge Cartesian product, A1, data A2, data n. It's no longer only this. It's quite a few, but still finitely many. So when you plug it in, they're all relatives of the Q multinomial coefficients. So once you simplify things, you get the Q multinomial coefficients times a certain fairly complicated rational function. For its dividend term, it's not complicated. It's a Q multinomial coefficient times a simple rational function in the QA1, QA2, But when you add up simple rational functions, you get a complicated rational function. And the computer can automatically, so in particular, we have also a conceptual human theorem that any coefficient of this famous q-Dyson product, not as a constant term, is a rational function times the Q multinomial coefficient. For the constant term, it happens to be 1, the rational function. But for other coefficients, it is some rational function. And the computer, the Maple program that I wrote, called q-Dyson, you can download on my homepage and you can play with it. And for any, well, not for any, if I want a coefficient of a million, x1 to the power a million times x to the power minus 5 million, and so on, a computer will refuse. In principle, it can do it, but it doesn't have memory, of course. But for small ones, it can do and get the rational function. And conceptually, we have that it's always a rational function. And this is also a kind of interesting. So this is basically the thing, but let me conclude in the last few minutes to prove the commentator used in that. So it's really beautiful. Trivial by hindsight, but still beautiful. It starts with a well-known, but not as well-known as it should be, theorem that if a polynomial of degree at most b vanishes at d plus 1 different places, it must be the zero polynomials. So suppose you have a polynomial, let's call it, I don't know, q of x, of degree less than or equal to 2. And it vanishes at d plus 1 places, then it must vanish everywhere. The beautiful trivial theorem. For the sake of completeness, let me prove it. Suppose it vanishes at a, 1, and 2, a sub d plus 1. By the Euclidean algorithm, you write q of x is x minus a1 times q bar of x plus the polynomial of degree 0, which is a constant. Since q of a1 is 0, you plug in x equals a1, so you get c equals 0. And q bar of x is the polynomial of degree from equal to d. That vanishes by this. So by the inductive hypothesis, this is true. Then comes the genius of Joseph Lagrange, who tells you for a polynomial of degree smaller or equal to d, how to reconstruct it from data. It's sigma I goes from 1 to d plus 1, p of xi times x minus x1, x minus xi minus 1 times x minus xi plus 1 times x minus xn divided by x sub I minus x1, x sub I minus, and so on. So this is the beautiful Lagrange interpolation formula. And why is it true? Because both sides are polynomial of degree smaller or equal to d. And the values, they are equal at x1, x2, xd. So hence it's true. Now you take the coefficient of x to the power d, and then to prove this, you take a typical monomial. So this is an immediate consequence, more or less, of this. The details are in this paper. So it all comes from the fact, from this simple fact, via the Lagrange interpolation formula. So in some sense, it's trivial, but it's beautifully trivial. Thank you very much.